Hello everyone, welcome back to my channel, and in this video we are going to discuss about the Peterson solution. It is a solution of a critical section problem. So I'm assuming that you all know about the critical section problem. So without any delay, let's get started. To solve a critical section problem, a solution needs to fulfill three requirements, which are mutual exclusion, progress, and bounded weighting. These three requirements to be fulfilled by a solution to solve any critical section problem. And what are these three requirements? Let's understand. So mutual exclusion. Suppose a process is executed in its critical sections, then no other process can execute in its critical section. Means that if two or more processes cannot be executing in their critical section simultaneously. Now the second point is progress. So in progress, if no process is executing in their critical section and some process want to enter in its critical section, then the decision taken by processes which are not executing in their remainder section, that and the decision is that which process will enter in its critical section. So this decision should not be postponed indefinitely. And the third point is bounded weighting. It means that how many times a process can enter in their critical section or execute in the critical section. So there is a bound or limit to execute or enter in the critical section. Means that there exists a bound or limit on the number of time that other process can allow to enter in its critical section after process has made request or before the request is granted to the process. Now we understand what is Peterson solution. So Peterson solution is a classic software-based solution of a critical section problem. It may not work on a modern computer architecture, but however, it provides a good algorithmic description of how these problems should be solved and illustrate the complexities in designing a software for the solution of critical section problem. Now the third point is the Peterson solution fulfills the requirement which are mutual exclusion, progress, and bounded weighting, which we discussed earlier. And the fourth point is in Peterson solution we require two processes which alternate the execution between critical section and remainder section. Now Peterson solution requires two data items to be shared between the two processes. First is interturn and the second is boolean flag. So interturn used to indicate that whose turn is to enter in its critical section, and boolean flag indicate that the process which is going to enter in its critical section is ready or not. So if we have a process pi, so if turn is equals to I, then process pi is a turn to enter in its critical section, and if turn equals to j, then process pj has turn to enter in its critical section. Now in boolean flag, if flag I is equals to true, it means that process pi is ready to enter its critical section, and if flag I is equals to false, then process pi is not ready to enter in its critical section. Now we understand the Peterson solution by its code. Here we discussed earlier that Peterson solution required two processes. So we have two process pi and pj. Here is the structure of process pi in Peterson solution, and here is the process structure of process pj in Peterson solution. So here we have do while loop. Inside the do while loop, first we have flag I equals to true. It means that process I is ready to enter in its critical section. But here we have turn equals to j. It means that the process pi is ready to enter its critical section, but first it gives chance to enter in critical section to process j. That is why the Peterson solution is called the humble algorithm. So here turn equals to j, then process j can next turn to enter in the critical section, it has process j. So now we have a while loop in which we have condition flag j ampersand ampersand turn equals to j. Means there is a turn to enter in its critical section of process pj, and process pj should be ready. But here we have flag I equals to true. Means here we have flag I and here we have turn equals to j. But here we have flag j and turn equals to j. So it means that the condition become false, and we move towards the next instruction, which is critical section. It means that process pi will enter in its critical section. Now what if this while loop has a condition true? So we can see here that here is a semicolon. It means that this while loop end here. It means if the condition become true, then we move infinitely between in this loop. That is why we have a false condition. So because of these two, we have a false condition, and we enter in the process pi enter in its critical section. After completion its work, flag I equals to false, that now process pi is not want to enter in its critical section. Here we can say that it is a bounded waiting, that once a process can enter its critical section, again next time it cannot be entered in its critical section again. Now the process pi will enter in its remainder section, and the loop will end. Similarly, we have a structure of process Pj here in Peterson's solution, but here we have flag j equals to true. Means that flag j is, it means that process j is ready to enter its critical section, but it gives turn to process I. That is why we have turn equals to I. But same like process pi, we have flag I ampersand turn equals to I. So we can see that the condition become false, and we enter and we move towards the next instruction, which is critical section. So therefore process pj will enter in the critical section, and after completion the task, flag j equals to false. Means after executing from the critical section, it cannot be entered in its critical section, and that is fulfill the bounded waiting requirement, and then it entered in its remainder section, and then the loop will goes beyond. Therefore, we can see that how process Pi and Pj alternate their execution in remainder section and critical section problem. So we can, by seeing this code, we can say that Peterson's solution is an humble algorithm. So I hope you all understand. Thank you for watching.